Nice to see all of you joining our first brown bag of the semester. So I'm Aisha Mahmoud. I'm co-organizing the brown bag with Maria. Dennis is on paternity leave, so it's just me and Maria this semester. But we have a really great lineup, and we're really excited for all the talks. We're excited to have Josh back as well, so that's nice to have him. And Michelle already introduced herself, but it's a real pleasure to have her at Berkeley. So we're gonna keep with our tradition that we've had the last few semesters, which is we'll have a student introduce the speaker, and then there's actually also a session. So if you're a student or a postdoc, hang around afterwards. There's going to be a 20-minute session, and Hiram has very kindly agreed to stick around a little bit longer so you can meet with him. And I'm just going to check with Michelle and Josh to see if there's any announcements that we should make. Anything? Good. Okay, great. Hiram, just before we start, do you want us to just, we'll type in questions in the chat, which is what we're doing, and I usually monitor that. If there's clarifying things, I'll interrupt you, but do you have any preferences? Should we just keep everything till the end?
No, actually, I would prefer if people ask questions as they go along.
Yeah, that sounds good.
It makes it a little more dynamic, and also it kind of keeps me on my toes and keeps me sane to know that somebody's paying attention and asking questions. Otherwise, I feel that I'm just talking to myself. So yeah, please feel free to interrupt.
Okay, great, fantastic. Okay, so I will keep an eye on the chat, Hiram. You don't have to worry about it.
That's great.
Or people can also, maybe if it's a burning question, unmute and ask. Okay, great. So we're very excited to have Hiram, and I'm going to pass it over to our master's student, Lauren, who's going to do the introductions.
Thank you so much, Professor. Hi, everyone. My name is Lauren. As was mentioned, I'm a demography MA student, and I'm very delighted today to introduce, on behalf of my cohort in the department, Dr. Hiram Beltrán-Sánchez, who is a community health sciences professor at the UCLA Fielding School of Public Health. Dr. Beltrán-Sánchez's research focuses on the demography of health and aging. He has written on health patterns and trends in low and middle income countries, on aging in high income countries, including issues about compression of morbidity, on the links between early life experiences and late life outcomes, and on the links between sociodemographic factors and physiological health indices. He co-founded the Latin American Mortality Database, which is the largest data repository of mortality from 19 countries in Latin America, and was a recipient of the 2018 PAA Early Achievement Award. Congratulations for that, belatedly. He's graciously agreed, as Aisha mentioned, to meet informally with interested students for about 20 minutes directly following his presentation, which is again in the same Zoom window. So please do join for that and take advantage of this opportunity to ask career and research related questions. So without further ado, I'll pass it to Dr. Beltrán-Sánchez as he discusses his work on biological age and its link with the aging process. So thank you.
Thank you, Lauren. Thank you for that great introduction. I appreciate it, and thank you for the organizers of this brown bag seminar. I'm very pleased and very honored to be presenting today on this forum. So as I said, please feel free to interrupt me as I go along. Let me know if you cannot hear me at some point. I switched to my headphones, so hopefully that makes it easier and better to go along. So great to be here, and excited to see that many familiar faces and people that I've known for quite some time, other ones who haven't had the pleasure of meeting in person, although I'm familiar with their work and their names. So very excited to be here in with this audience. So what I'll be presenting today's work in progress that I've been doing with my colleagues at the University of Wisconsin-Madison, with my long-term collaborator, Alberto Paloni, and a couple of other collaborators, Mary McInerney and Jiyue Yunfang. So what we are working on is what we call modeling biological age, and how we can link that indicator with the aging process, and I'm going to be focusing my background in demography, so I'll be focusing on what we could do at the population level. By population, I mean usually national level populations, not necessarily epidemiologic studies, which I'll touch upon a little bit on that. So a little bit of background. There have been several indices that have been proposed to try to get at the idea of underlying biological and physiological deterioration that happens in the body. The idea behind is to have indices that work better than chronological age. So throughout the talk, I'll be using the acronym CA to refer to chronological age. That's a little bit different from what we use in demography, that we usually just call it age. But for these purposes, because I'm using the concept of biological age, I'm going to refer to it as CA. So the idea is to have these kind of indicators that ideally would be a sort of a better proxy for what happens to the individual's physiological and health status as we age. So most of the common indices that have been developed early on, and I'm thinking a few decades ago, are focused on particular physiological systems. For instance, the Framingham Index that takes a look at the long-term risk of cardiovascular events, or the metabolic syndrome, which is an indicator more of the metabolic functioning, or more recently indicators along the lines of the allostatic load that try to take into account also the stress response. The computation of these prior indices tend to be somewhat simple. Part of the reason is they try to be used in the clinical setting. So by using in clinical settings, they have to be somewhat easy to use. For example, the Framingham Index is a score that depends on a number of indicators that are usually treated as continuous, and they are just dichotomized and then summed up to get an index. The allostatic load is traditionally computed by a count of binary indicators that are transformed into Z-scores and give us a sense of in a range of how likely that individual is going through these allostatic load processes, or the metabolic syndrome, which is just a count of usually 5 or 6 physiological markers, including lipid levels, blood pressure, glucose levels, and each of those indicators is ranked in the range of high or low risk. And depending on that risk, then the values are summed up. So biological age, on the other hand, has been constructed somewhat different. And part of the reason is that we are usually thinking of biological age sometimes referred to as aging clock. And these aging clocks are not necessarily linked to a particular physiological system. So what we think of biological age is kind of the underlying biological and psychological deterioration, physiological, I mean, deterioration that might occur in the body as we tend to age. And when one tries to get an indicator of the physiological deterioration, we think of getting this biological age under different domains. Sometimes we use biomarkers of physiological states, which are like lipid levels, for example. Sometimes we might want to use genetic indicators, such as telomere length, one of the possibilities, or perhaps indicators of cognitive decline, neurodegenerative activity. Or more recently, people have been using epigenetic modifications as part of trying to get into the idea of computing these different processes as we age. However, again, because I'm focusing more at the population level is until very recent that we have been collecting biological information to get some of these markers. So most of the indicators that have been developed at national level or in large surveys tend to focus only on 2 indicators, usually physiological states, sometimes epigenetics, which is the more recent development, and sometimes they try to combine them. So what I'm gonna show you today is on methods that are traditionally used for physiological states. I'm not gonna focus yet on epigenetics. I'm gonna touch upon a little bit that later. But what I'll be focusing is on physiological states for estimating biological age, and I'm gonna make the point later why it is important, I think, to focus on this before we then move on to the combining information with epigenetics. So for instance, one of the early methods to compute biological age was using multiple regression since the early 80s. So the idea was fairly straightforward. You have a set of biomarkers on the right-hand side. You use age on the left-hand side, create a regression equation, predict the values from here, and that's the predicted value for biological age. A second approach was, let's try to use the idea of data reduction. So we have a bunch of biomarkers, let's put them into a principal component approach. Usually when people do this type of approach, take only the first component, even though we might end up with several axes, but usually people take only the first component, from which then they construct taking the factor scores, which are usually unitless indicators, And they reconstruct kind of the standardization process to get an idea of getting a biological age extracted from the biomarkers that were included. The most recent method that was developed a few years ago, and this is the one that is still in use nowadays when people try to combine physiological markers with some epigenetic indicators, is a method by Clemmer Duval. And this is a two-step process. In the first stage, they estimate a series of bivariate regressions. So on the left-hand side, you have the biomarker. On the right-hand side, you have the chronological age. You get a bunch of bivariate regressions, as many as biomarkers. You get all these coefficients that you later are going to combine into the indicator of biological age. So this is a somewhat more elaborate process. It's a two-step process. So when one combines the slopes from all the bivariate regressions, we end up getting something along these lines, a little more elaborate process to get biological age. But the underlying idea is bivariate regression, that somehow the slopes are going to be summarized and combined to get us a single result. What we are proposing in here is a slightly different way, perhaps, of looking at this biological age. First, the previous methods mostly rely on this strictly linear association between biological age and chronological age. The second is that one of the recent methods, the one that I focus on, Clemmer Duval, not only linear, but is a little bit more than that in the sense that they constrain the linear association. For instance, one of the constraints of that method, of the underlying assumptions, is that the intercept and the slope are one. In other words, if one looks at the association between chronological age and biological age, it goes through the origin, and chronological age increases by 1 unit as biological age increases. So it's a one-to-one association. So it's a very peculiar and particular linear association between the two. Our goal, with what I'm going to show you today, our goal is to try to generalize the approach of linking this biological indicator of BA with chronological age. And what we are proposing to do is through a structural equation model. Rather than doing this simple single bivariate regression, we're going to put in a structural equation model. Under this approach, our indicator of biological age is going to be an unobserved latent construct. We don't know what that is, but we're going to link that unobserved latent construct with a set of biomarkers. And at the second stage, when we could also link it within the structural piece of the model with chronological age. The last piece that we also want to improve upon is on relaxing the linearity assumption that is traditionally used between chronological age and biological age. For example, I'm going to show you one case in which one can think that the association between biological age and chronological age is non-linear, is, for instance, a log linear association, or in other words, the increase in biological age is exponentially associated with chronological age. By using this type of approach, we argue we are able to relax that assumption. And also, actually, what is, I think, is important in the way we're thinking about this is that we do not constrain the values of the parameters. Instead, we're going to empirically estimate the parameters, and then we're going to test whether the null hypotheses are rejected. For example, in the case of the nonlinear model, if one rejects the assumption that the slope in here, this exponent, rejects the underlying hypothesis, this is 1 and this is 1, this basically reduces to the Clemmer-Duval assumption, in which this is a one-to-one relationship. So we believe it is a little more flexible to do it that way. So just very quickly or very broadly define, this is kind of the idea that I'm presenting, which is what I want to have an structural equation model. This is generally how one defines this type of models. We have a set of biomarkers that are going to be related to a latent construct, and in here comes at the higher level the association with chronological age. I'm going to show you two flavors of this model. In the first kind, we have a linear function relating chronological age with biological age, and in the second model, we're going to have a nonlinear association between chronological age and biological age. Now, when one computes types of models, we could predict a factor score that comes from the structural equation. This factor score is a unitless indicator. So one can think of this unitless indicator as this conditional mapping of the vector of the unknown biological indicators onto a vector that represents chronological age and is going to represent a ranking on the underlying physiological deterioration of physiological status. In this case, I'm thinking of physiological status because those are the markers that I'll be using. So what we are going to proceed then is to try to put a number to this unitless indicator. And in order to do that, we're going to do it in two different ways. One, which is what we call the outcome-free estimator. I'm going to show you what that means. And the second, what we call the outcome-dependent estimator. So here is the first idea. The first idea is we have a set of factor scores that come from a structural equation model. And then we're going to just simply regress those with chronological age. And what we end up getting is the predicted values from this association with is what we will call the biological age. So this is a way, in some ways, to anchor our underlying unitless factor scores. In the case of the nonlinear case, the association is similar. It's just that we are now in the log linear approach. So again, we get a factor score associated under the nonlinear method, in which case we then try to predict what the biological age would be. The second approach is what we call the outcome dependent. And I think this is the one that is perhaps a little more exciting. And here is one proposition that we have. We could actually have many outcome dependent estimators. So in the case of mortality, which is what we are looking at as the outcome, what can do is estimate to Gompertz proportional hazard models. One can estimate any other type of hazard model, but let's start with a Gompertz proportional hazard model. We have one model in which only includes age, and we have a second model in which we now include, in addition to age, the factor score. We predict a hazard rate from here, we predict a hazard rate from here, and that's how we're going to be able to anchor our value of biological age. So if a factor score is associated with a deterioration which increases the hazard of death in here, the predicted age would be much higher than if this factor score is within the lower rank of the underlying physiological score, in which case the mortality rate would be lower and would lead to lower biological age. What I think is interesting about this outcome dependent is that one could potentially tailor the underlying physiological deterioration to an outcome. In my case, my interest in mortality, but I might as well predict the outcome perhaps through health indicators such as chronic disease, such as the incidence, and so on and so forth.
Could you explain what T is here? Is it the same as chronological age, or is it something different?
This is time that elapsed from the baseline until the mortality follow-up, because this is the time is on the x-axis, so I'm following individuals over time. I'm going to be using n hens at the mortality follow-up to fit my proportional hazard model.
So it's like a period effect?
Not really, because when we fit this type of survival models, we need a unit that measures the time that has elapsed as we observe individuals under the mortality risk. In my case, the time that I'm using to observe those individuals is from baseline up to follow-up. That is my T. Does that make sense?
Not really. On the right-hand graph, you have something that looks like the mortality by age.
Right.
It's mortality by time conditioning on age, so I don't understand that.
There is the same in here. This is also mortality on time conditional on age. It is the same in here. The only difference between these two models, this one controls for the factor score that came from the structural equation, this one doesn't.
How do I stay the same age as time is passing?
Oh, that's kind of the idea. The idea is under the assumption that there is no underlying physiological deterioration and I only use age, I'm going to predict a hazard. Once I control for the underlying deterioration, because remember, each individual is now going to have a factor score. So we would predict a mortality rate associated not only with age, but also controlling for the factor score that the individual got from the structural equation model. So once we control for that, the hazard rate predicted from this equation could be higher or could be lower relative to the one that one would predict without the factor score. So let me, in terms of time, let me go on, but then I'll come back if it's still a little bit unclear, Josh, if that's okay with you. So for the data, to test this kind of idea that I just described, having this structural equation model with two flavors, linear and nonlinear, and then anchoring those values into the outcome-free and outcome-dependent, we're going to use the N-Haynes data. Part of the reason of using the N-Haynes is because it's one of the surveys, national level surveys, that has the most comprehensive set of biomarkers. So I'm going to use, the NHANES, and I'm going to look at people between the ages 30 to 75, and then I'm going to be looking at the mortality follow-up in 2015. That's going to allow me to then anchor or get a number to that biological age under the mortality outcome of interest. The biomarkers that I'll be using are biomarkers on 6 different physiological systems related to metabolic function, cardiac function, lung, kidney, liver, and some of immune and inflammation. So these are in total about 9 different biomarkers. So I use those biomarkers, and I'm going to show you a set of results. I'm going to show you 4 types of results. One set of results is once we get the underlying biological age estimated from these different approaches, we're going to see what's the link between biological age and chronological age to try to assess whether the link is 1-to-1 with intercept of 0, as the Clemera-Duval, for instance, assumes, and what will happen in the other cases. And then we're going to look at the association between the biological age we predicted with our approach and how that links by race, ethnicity, sex, and education. And then towards the last part of the results, I'll show you, given that we are linking our outcome-dependent measure with mortality, we can compute 2 types of compared slopes from which we could compute the mortality rate doubling time, and then associate how much of the excess mortality could be due in some ways to the underlying physiological deterioration. And finally, I'll try to make some links with biological age and life expectancy at age 65. So with the first set of results, very quickly, here is just a snapshot of what would obtain from the structural equation model. I'm not going to go too much into the details of the model because, as you can imagine, these are only the coefficients. In a structural equation, we also have the variance components. The point that I want to make in here is that when we fit a linear on a nonlinear structural equation model, the fit seems to be a little bit better under the AIC or BIC indicators under the linear approach, although the values are not that different. So this is just to show that one could have different flavors of associations between age and biological age, that they don't have to be necessarily linear. So if we get the age pattern, which is something that we in demography kind of like to do, here is the age pattern of the predicted biological ages under different models. So the gray line, which is somewhere in here, is the density that one would obtain directly from the chronological age. The black line is the one from Clemera-Duval, which is right here. And then we have the multiple regression, which is here. Here is the principal component. And then we have the results from the outcome dependent and outcome free. The outcome dependent are the red ones. The outcome free are the green ones. If you see a solid line, that is the, I'm sorry, let me go back. If it is red, is the structural equation linear. If it is red, it is structural equation non-linear. So within the linear, we have the outcome dependent, which is the dotted line, and the outcome free, which is the solid line. So in essence, here are the 2 solid lines. These are the outcome free estimators. Here are the 2 dotted lines, the outcome dependent estimators. This one in here is the outcome dependent. This one in here is the outcome free. So what we see, just generally speaking, is here is the one of the common methods, which is the black one. That one is in between the outcome free and the outcome dependent. So depending on how one models this, the Clemera-Duval is kind of falls in between. The method that we propose moves data a little bit to the left if they are younger, and a little bit more to the right if they are older. So there are people who are younger chronologically speaking who would have become a little bit biologically younger, and people who are chronologically older who will become biologically older. So I'm going to show you that in a figure, which is this. So here is the association between chronological age, which is on the x-axis, and biological age, which is on the y-axis. This is for males, this is for females. And here is the association between those for the Clemera-Duval, the multiple linear regression, or the principal components. So as we already know from the assumptions of this method, the slope is 0 and the intercept is 1. I mean, the slope is 1. That is the assumption that that method does. By design, that this regression goes through the origin, and 1 increase in age leads to 1 increase in biological age. In contrast, these are the 2 methods, say multiple regression of principal components. will imply that although biological age increases, as age increases, the increase is not on a one-step increase, it's slightly lower. If one uses the outcome-free estimator, what we would obtain is, again, this intercept is different from 0, and this slope is different from 1. So this is one of the advantages that I was describing early on, in contrast to this method that by design restricts this slope to be 1 and this to be 0. In our case, this intercept and the slope could be technically anything depending on the data, or could vary by method. If one uses the outcome-dependent approach, what we would find is, again, different slope. The slope is different than 0, but perhaps more interesting, now the slope in this case is greater than 1. So under the outcome-dependent, one increase in age is associated with a faster increase in biological age, in contrast to these other methods that would predict that although biological age increases with age, the increase is not one-to-one. If one associates this biological age with indicators by sex, race, ethnicity, and education, this is one way in which we think would be interesting of addressing those associations, which is let's compute the difference between biological age and chronological age. When this is positive, that means there is a faster aging, meaning there is higher biological age relative to chronological age. So what we are saying in here is, let's see how the X's, biological age relative to chronological age, associates with sex, race, ethnicity, and education in this particular sample of the NHANES. Something that I want you to take note of is if one uses this method, one would obtain that the chronological age increases in chronological age do not link with X's on average of biological age. So on average, this is 0. And you would obtain that there are no sex differences either. If we use one of our approaches, in particular the outcome-dependent approach, we do in fact find that increases in age are associated on average with largest increases on BA relative to CA, and that we also find sex difference indicating that females, although it increases for both male and females, the increase in biological age on average relative to CA is slightly lower among females than males. And if one uses this model, the outcome-dependent, the fitting of the data is much better than when one uses any of the other approaches. So we think this is a quite important distinction, that under this approach, we are able to identify differences by sex and differences with age, chronological age. The last piece of results that I wanted to show you, well, this is one more after this one, is what we call the mortality rate doubling time. The essence in here is, what if we fit a Gompertz model that only includes age? This is the slope that one would obtain. What if we include a Gompertz model that now includes as an indicator the factor score from the structural equation model? This is the slope for age that one would obtain. So for instance, if one looks at this value, here is the slope in the Gompertz model that one would compute with only age. With this slope, the mortality doubling time that one would compute is about 8.6 years. If one includes now the factor score that comes from the structural equation model, that slope goes down to 0.052, which means the doubling time would now be 13.2 years. The difference between these two, which is about 5 years, is about 54.2%. So this is what we would say. This is about the change in the mortality rate doubling time that could be attributed to the physiological deterioration, in this case, captured by the biomarkers that we included in our structural equation model. And if one looks at that contribution, one sees that Hispanic Blacks and Mexican Americans have a much larger aging that could be attributed potentially to the physiological deterioration associated with the biomarkers that we have included in our model. And among non-Hispanic whites, that'll be a lower contribution. Similarly for
so I understand the 0.52. That says if you could hold constant all of your biomarkers, that the rate of aging from everything that's left out of those, just from age itself, would be 0.05?
That's correct.
Okay.
That's correct. Exactly. So this is why I was mentioning early on, once we use an outcome to get a sense of the underlying factor score that comes from the structural equation model, in our case, of using mortality, allows to start making these types of connections that we had used in demography for quite some time about this mortality rate doubling times, and try to appropriate or assign in some ways how much of that aging could potentially be due to this underlying physiological deterioration, which is captured by our factor score from the structural equation model. The last piece that I wanted to show you, this is what I just described. If I were to look at these values, physiological deterioration would account for more than 50% of the aging among these non-Hispanic Blacks, and about 2/3 for Mexican Americans, and just about 1/5 for non-Hispanic whites. If one uses this to predict mortality, which is one of the areas that we sometimes are interested in doing, this is by computing the area under the specificity from the survival model under different specificities, whether one wants to be between 80 and 90% precise, between 90 to 100% accurate, or between any range 0 to 100. The outcome dependent seems to be more predictive for the risk of death, which in our case perhaps is not surprising, because we actually train, if you will, we train this outcome dependent to be as a function of the mortality risk. So it has a much better predictive power. The last set of results that I would like to show you is we computed life expectancy at age 65. So here is the idea that let me walk you through this diagram. So we have females on the left, males on the right. We have the different methods in here in different colors. So on the x-axis, what we have is numbers from 0 to 5. That means biological age would be between 0 to 5 years older relative to chronological age, or between 0 to 5 years younger relative to chronological age. And then what we would do is we will compute life expectancy for each of those cases, and then compare that with the life expectancy of individuals in which biological age is exactly the same as chronological age. So what this shows is this quadrant represents younger biological age and longer life expectancy, and this represents older biological age and shorter life expectancy. How long and how short life expectancy would depend on the method, and would depend on how younger and how older one might be biologically speaking. So for example, if one looks at these results in here, these are results pretty much for all the methods, except these two are from the outcome dependent. So what this shows is if one computes biological age under the outcome dependent approach, the younger the individual, the much larger the difference in life expectancy would be relative to somebody who did not have this excess physiological deterioration, meaning the biological age is equal to chronological age. And the differences could be as large as close to 70% difference in life expectancy, or 70% higher life expectancy if one is on average 5 years younger, or it could be in the range of about 55% lower life expectancy if one is about 5 years older. Biologically speaking, this is the case for females. The other methods would be, although they would also predict reductions in life expectancy or increases in life expectancy, those reductions or increases would be much shallower. So to conclude, and I think it's going to give us enough time for discussion, this is some of the items that I would like to take as take-home kind of messages. That in this case, a nonlinear function or a linear form with a slope different than one seems more suitable to estimate this biological age. We think that we don't have to impose parameter constraints, as some other methods do, in particularly the Clemmer-Duval. We can actually test whether those parameter estimates are needed, or those constraints. If we predict these values, the age pattern is somewhat comparable with what other methods have produced, which means our values are somewhat reasonable. In the case of the outcome dependent, is definitely more predictive of the risk of death. And the outcome dependent method is going to allow us to look and to include different dimensions of aging that results in models that, in our case, fits the data much better. In particular, in this case, I just show you two very simple flavors, the linear SEM and the non-linear, which is basically a log linear association between chronological age and biological age, but there is no reason why we couldn't use any other type of functional form relating biological age and chronological age. The next set of items that I think would be important in the case of the method that we're proposing through this structural equation model, we believe it is more flexible and allows for fairly generalizability in terms of the indicators that could be included. Is producing mortality estimators, which in our case are mortality related, which are quite predictive. We think it also allows to get a rich interpretation of these indicators, as in the case that I showed you with the mortality rate doubling time, or with the case of life expectancy increases or decreases, and could allow us to get these deterioration processes, and as some people have called it, accelerated aging. And the outcome dependent in particular, I think opens the possibility of testing the existence of these biological processes on different biological systems, and to link that to perhaps even specific outcomes. For example, we might have biological indicators that might be very predictive of a cardiovascular outcome or a metabolic disease. Or in the case of aging, there might be indicators that are fairly predictive of physiological functioning or disability, which might not necessarily are related to high risk of mortality. For example, arthritis is a condition that is highly disabling and highly predictive of functional mobility, and yet is quite its risk of mortality is very low. So in other words, one could be biologically older or younger, depending on the outcome that one is looking at. So I think this outcome dependent allows to start getting a little bit more into looking at different outcomes or perhaps different systems. So I think I'm going to stop here to open it up for questions.
Thank you. Thank you very much, Hiram. That was really wonderful. So we have a few questions in the chat, and then I'll just ask folks to maybe unmute and ask their questions. Ken, do you want to ask your question?
Yes, hi, Hiram. Very interesting contribution in a very active field. Some of us, you went very quickly though, and at least one of us, myself, was lost.
I'm sorry.
The part that Josh was talking about.
I'm sorry.
How
okay.
the Gompertz model came in, and so I wonder if you could step us through an example of that equation where the hazard, as you wrote it, mu, the Gompertz hazard mu of t conditional on chronological age and the factor score was to be equal to mu of t conditional on chronological age double prime prime there. Could you, so Gompertz model is going to have a slope and intercept parameter. I really couldn't figure out what the quantities were in there. So could you just spell some of that out for those of us who weren't following?
Yes, let me.
The conditioning, what's the T,
yes.
What's the sort of basic kind of.
Let me give it a try, and I actually have in here.
Okay, good.
So here is perhaps you want a more formal description of what I could perhaps provide verbally. So here is the idea. We have one of these Gompertz hazard model, one that depends on chronological age and the other that depends on age and also the factor score. So here is the first model. So we have T, in this case, T is the time that elapsed since the individual was first observed. So in our case, the first time the individual was observed, it was 98 to 94. And the follow-up goes until 2015. So this T is measuring that time that has elapsed since the first observation, 88, 94, up to 2015. So here is the first model, the Gompertz one. And here is the second Gompertz, in which we now have included a factor score in the equation.
Okay, so I'm already lost. So you're assuming I don't know what you're assuming. Chronological age is chronological age when? At observation or at baseline?
Exactly, at the baseline observation. That's correct. Exactly.
Okay. And so
Yes.
T is then the time. So CA plus T. No,
In this model,
you're
what we
assuming
can,
a Cox proportional hazard on duration since observation. Is that what you're doing?
yes, duration since observation, that's correct. Because in this form, you can see there are two betas, but what we end up doing is we're constrain these betas to be the same. So a different way of thinking in the way we usually do it in demography, we switch the axis observation, and instead of doing age,
Yeah.
I'm sorry, instead of doing time from observation, we use age at baseline, and the time in that case is age at end of observation or
Yeah.
age at death.
Okay, we're with you at that point.
So,
and then you have your factor score is then another Cox proportional.
It's going to be another variable in the Cox proportional model. If I were to take the logarithm of this, which is how we usually fit this Gompertz proportional hazard models on the log of the mortality rate or the log of the hazard, this becomes a linear function, which in essence says we now have a new added covariate that we included, and the added covariate is the one that comes from the factor score from the structural equation model.
Okay, this is helping.
Okay. So then we say we predict the value from this equation, meaning we predict the hazard rate from that equation, and we solve for the BA, meaning the biological age, in the first equation. So in other words, what we are saying is here is a model of mortality taking into account the factor score. Here is a model that does not take into account the factor score. If I were to predict a mortality rate from here, what age would the mortality rate would correspond to in this one?
Okay, so
does that make sense?
Yes, it does. Now,
so what this means is if the factor score that one obtains in an individual is such that this factor score is in the high ranking of the scale, meaning that individual had perhaps physiological deterioration, the corresponding hazard rate that one would predict in here, once I put it back in, he would be associated with an older age.
Okay, so it's a shift measure. Really.
It is right, and that's what I was saying. This is, I think, what makes this outcome dependent interesting, because in my case, I'm kind of training, if you will, my biological age to the outcome of mortality. In other words, what I'm saying is, given the physiological deterioration that was captured in my structural equation model, if I were to predict a mortality rate, would that rate would be higher or lower if I do not take into account the factor score? And that is the age that I'm going to be calling biological age. So that biological age would be, again, tailored to the outcome of mortality. But as you can imagine, one might actually use the same approach to say, what if I'm not interested in the risk of death, but I'm interested in the incidence of a cardiovascular event, or in the incidence of, say, disability? Then I could potentially follow a similar idea and say, given the underlying factor score that I computed from my indicators, what would be the risk, or what would be the rate at which this individual could get the incidence of this particular physiological outcome? And then would that place that individual at a higher or lower risk given the set of biomarkers that I use? So that opens the possibility for using this in this way of developing this for mortality, in which case one individual could perhaps be biologically older for mortality, but might not necessarily be biologically older for developing physical functioning, for instance.
Okay, good. Thank you. I'm happy. I hope
Thank
others
you.
are.
Thanks, Hiram. Maybe Ron's question is maybe a good follow-up one. Ron, do you want to ask your question?
Go ahead, Ron.
Okay. Whoops. I thought I had.
You kind of show
Am I
for a
not?
second.
We can hear you.
But can you see me? No.
No.
I don't know. I can't seem to unmute myself. Video,
well, I can hear you.
Okay, I'll talk. Yeah. So when you were showing that comparison and I guess the proportion of the increase with chronological age that could be accounted for by physiological state. I think something like that, and we had proportions.
Right, the
I'm just
mortality rate doubling
wondering,
time.
if we think about the effect of chronological age, is there any way it can affect mortality other than working through changing physiological states? As we look at those proportional, those shares that of the age of the association with age is actually accountable by physiological state, should we think of that as just, well, these are those are the only physiological states that you've included in the model? But if we had a completely comprehensive accounting, there'd be no chronological age effect left at all. Is that?
Well, I don't know. I don't know, and I think that's actually a very interesting question, Ron. I don't know if that would be the case. In other words, I don't know if by adding this set of additional indicators, we indeed eliminate the underlying contributing factor, just the passing of time, which would be in this chronological age.
Yeah.
I'm not sure.
For example, it was very striking that the white women had a very low share of the mortality effect arising from physiological deterioration, as I recall.
Yes.
But I suppose it might be that you'd get a different result if you had included other physiological states.
That's correct, and I think that's one of the pieces that I wanted to discuss towards the end. At the beginning of the talk, I said I was going to focus on these indicators of physiological outcomes, which are these biomarkers that I use. But we could, using this approach, include epigenetic indicators. And we do include epigenetic indicators. We're capturing an additional dimension of the aging process.
Yeah.
Which I'm not capturing in this case, but we might as well add not only these epigenetic indicators, we want to go even lower levels, we can use any other types of indicators that are more at the cellular level. Nowadays, people are using proteinomics, which is our certain proteins that are measuring, exosomes, which are also some indicators that are using. I mean, I think opens up the possibility for controlling 4 different levels of the physiological system. In the case that I'm doing now, it is sort of the ultimate physiological outcomes, if you will, which is I'm using biomarkers of indicators that are already measured in the blood samples. But some of the epigenetic markers could be indicators of methylation in certain regions of the genes, but those might not yet have perhaps translated into a physical outcome. Right. So yes.
Okay. Thank you very much.
Sure.
I really enjoyed the talk.
Thank you.
Maybe we'll take a few more questions. Will, did you want to make your comments?
Yeah, sure. Thank you, Hiram. You always have a really important contributions to these literatures, and I really enjoyed the way that you're sort of modeling this. I put in the chat that a couple of years ago I published with co-authors a much more simplistic analysis of the type that you were referring to before, where we're sort of measuring either age or time to death on a number of sort of biomarkers. But one of the things that was interesting coming out of that is that we found very different patterns, as you'll see it, by gender, but also by education. And then we were comparing across different countries. And we found very few consistent measures across contexts. And I think that this, again, just sort of calls into question the interpretation of what we're doing. So there are people who are trying to look for these universal biomarkers of aging, but I think that these really are so dependent on the context, both the social environment, which feeds into mental health aspects that someone put in the chat, and as well as access to medical care, et cetera. So I would encourage you to take some other data set from some very different place and run these models again. So we were comparing NHANES and HRS with them, lots of markers with Costa Rica, for example. And we just found such different relationships. And so I'd encourage you to do that as you're pushing this forward.
Thank you, Will, for your comments. And yes, indeed, that's what I'm working on now. I'm using HRS, and I'm also using MHAS in Mexico, the Mexican Health and Aging Study. They collected blood samples in 2012. Not that many, but it would allow us to perhaps try to get at something. But
I would go to Taiwan or Costa Rica or one of the other places that has a lot more markers.
Yep. Yeah. So definitely this is one area that I'm very much interested in, also pursuing this possibility of looking at different contexts, which I agree. What I presented today was kind of the early work in the sense of getting more at the computation and the thinking of how one goes about trying to get this biological age. But there is indeed a second part, which is how we start linking and making sense of some of these differences in biological age. Mm-hmm.
Okay, let's do one more quick question. Josh, do you wanna go?
No, thanks. I already asked my questions. It's fine.
Okay, anyone else have thoughts, comments, questions? Okay, great. Well, let's unmute and thank Hiram for a really wonderful talk.
Thank you, everyone. I really enjoy. I'm glad you guys asked all these very interesting questions. Thank you for coming. So